quickly go over three quadratic functions and their properties as a supplement for what we go over in class, so you can refer to this video at any time. Some things that you should already know from Algebra 2 is know how to get x and y intercepts solving quadratics. You should also know how to graph transformations. Completing the square we did earlier this year, but we're going to pick it up again because it's a strategy on solving quadratics. So let's go ahead and get started here. A quadratic in standard form is ax squared plus bx plus c. A cannot equal 0, and the domain is all real numbers. The reason why a can't equal 0, it wouldn't be a quadratic then. This would cancel out the x squared, and it would simply be a linear equation at that point. If you recall, the parent function for x squared looks something like this. Vertex is at 0, 0. Table, vertex is in the middle, so I would take the number right before 0, and I take the number right after 0, and I square it, and I get, this is plus 1. I get 1, and then I get 1 here. I could also pick -2, pick 2. So the axis of symmetry here is right down the middle, splits this parabola in half, equal halves. So whatever on this side for its y value will be duplicated on this side for its y value. -1, 1, therefore +1 yields 1. If I put 2 in here, you would get 4. So I know, reflecting over the axis of symmetry, that -2 also yields 4. Likewise, we can do the same with all quadratics if we know a few essential things, which I'll illustrate down below. What happens when the quadratic becomes x squared plus 2? If we look very closely, this can be rendered in vertex form, which would give us f of x equals x squared, which really means x minus 0 squared plus 2. I know my vertex will be now at 0, 2, which means I have no horizontal movement at all. There is no horizontal movement from the parent function, and there will be a vertical movement of up 2. So the parent function would move up 2. What if we had the quadratic look something like this? You should all now recall that I have a horizontal and a vertical. This is my h and k for the vertex. It should be all review now. I know that this is a plus, and it turned from the vertex form from minus to plus. So this has to be a negative. So I know my vertex will be -3, 2, or a horizontal movement to the left of 3 from the parent function, and then up by 2. The axis of symmetry is equal to the x value. X equals -3, and it splits it right in half. So you can reflect your points from either side, from left to right, so you don't have to figure out both sides. You figure out one side, and it's perfectly equal for the y value on the other side. Okay, let's continue. As I discussed, this was in vertex form. Let's discuss what A does. This should be review as well. If A is negative, the parabola is turned U-shaped upside down. If A is positive, if you recall, it's smiling. So positive, smile, negative, a frown. If the absolute value of A is greater than 1, the parabola rises faster. So what it will do will be a thinner shape, either U-shaped up or U-shaped down. If A, the leading coefficient, right here, is a fraction or between 0 and 1, it will rise slower, meaning the y value will rise slower because this is equal to y. That y value, because of that a value, is going to be affected. So this will now, in effect, cause it to rise slower or be wider, U-shaped up or U-shaped down, depending on if it's a positive or a negative. So how do we get quadratics in vertex form? We usually end up having quadratics that are not in vertex form. If they are, then you're able to establish what the vertex is and reflect points on the axis of symmetry. Typically, we try to get quadratics into standard form and then turn them into vertex form. So I'm not going to read through all these steps. I'm going to actually carry it out on an example on the next page. But if you read through these steps, when you're doing a transfer of a standard form to a vertex form, you can go by these steps. We've done this once before this year, so I'm sure this review will be helpful. So let's take an example. Let's take a look at this quadratic. This quadratic happens to be in standard form already. ax squared plus 8x plus 5. However, time to time, you may find that I end up with something that looks possibly like this. 2x squared plus 8x equals negative 5. In order to put it in standard form, I'd move that 5 back over here. Likewise, the 8x could be over here. So the quadratic could be on different sides of the equal sign. What you want to do is make everything on one side. Typically what I like to do, though, is whether it's on the right or left, I like to have this leading coefficient to be positive. So let's go ahead and start. This is already in standard form, so this is f of x equals 2x squared plus 8x plus 5. It's already in standard form. So the next thing we do, if you look back on the previous page, is we move the c value, that's not standard form, ax squared plus bx plus c. This is standard form. We move the c value to the other side. So what I'm going to do is what I did up here. So 2x squared plus 8x equals negative 5. Now what we want to do is get this a value to be 1. I want to get rid of it. So what I have to do is divide everything by that a value. So this is going to now be 2x squared plus 8x equals negative 5, all divided by 2, which will yield x squared plus 4x equals negative 5 over 2. Notice that I left space here. The reason why I left space here, if you recall when completing the square is you're going to add a number to this spot here. If you add a number or subtract a number, it could be, you will need to do the same thing on the other side of the equal sign. Now, that number actually lets us turn it into a squared, which we get vertex form. So we're going to get something like this. This h could be positive or negative, so it's going to change that sign possibly. We're going to get something like this. Okay? So let's go ahead and see what we have to do to complete the square. In order to complete the square, what I'm actually going to do is I'm going to add b over 2 squared to both sides. Now, if you look closely, this is the b value. Here's ax plus bx plus c. That value right there is what we're looking for. So I'm going to now take this b value and I'm going to divide it by 2 and square it to both sides in order to complete the square so I can turn it into something that looks like vertex form. So b over 2 in this case would be 4 over 2 squared. Now I leave it like this so I know what step I've come from, and I know that this is b over 2 because it's easily to mix these numbers up when we put them in the parentheses. So I'm going to add 4 over 2, which is 2 squared, which is 4, to both sides. So let's do that. So I'm going to add the 4 over 2 squared to both sides. And this is negative 5 over 2. Now you'll see here I left it as well in fractional form on the right side, which is good because I have a fraction that I'm going to need to add it to on the right side. So let's see what happens now. Now what actually happens is because this is a square now, this is a perfect square. It's a binomial square, however. What it turns into is x plus whatever b over 2 was. And this is squared. So this whole piece turns into this. Now notice this b over 2 is inside the parentheses, and this square does not follow it. So we just take this b over 2 value right here. Now this b over 2, this, depending on what the value is for b, it could be negative, would turn this binomial into a negative. In this case, we know our b over 2 is 4 over 2. Excuse me. So that's what I'm going to do now, is x plus 4 over 2. Now I'll later change this. I just want to show you that it's the same number that we brought down. Okay, this whole thing changes to this now. Equals, now I'm going to actually multiply this out. This is negative 5 over 2. Plus, well, this is 4 over 2, right? So that's 2. 2 squared is 4. But I want this with a 2 as a denominator. So how do I get 4 with a 2? Well, that would be 8 divided by 2 is 4. Now I can add these two together easily. Now what you'll find out is that I can now transform this to x plus 2 squared, and the other side will now become 3 over 2. Now if you look back in your notes, I think it's somewhere between 5 and 6. If you have a fraction on this side, what you'll need to do is you're going to bring this number over to this side, which will help us to understand what the vertical movement is. But if I'm dealing with a fraction, I can simply get rid of that fraction by multiplying by the denominator. So I'm going to multiply this whole thing by 2. So I'm going to multiply this by 2. What we end up with is, this is the a value now. So this is 2 times x plus 2 squared equals 3. Now what I'll do is I'll bring this over to the other side now. which will give us our vertex form. And as you can see, the vertex is going to be 2, -3. Or, excuse me, this is going to be -2 because it changed signs. So the vertex is -2, -3. So let's follow up with some more properties of quadratics. You should already know and feel comfortable with the parent function, or any parent function that we covered in the last chapter. You should know that the a value stretches or compresses it vertically if a is not equal to 1. If it's 1, it does nothing. It looks like the parent function. Okay? And your horizontal moves are your h's. Your vertical movements are your k. Okay? You should know how to plot your vertex, and you should know the axis of symmetry. The axis of symmetry just really is x equals whatever the h value is, and then that splits a parabola in a perfect half, which actually helps you to plot points either on the left or right. I don't have to figure out in a table what one side is if I just figure out the other side. So if I know this side is an x value, I know the corresponding x value over here will yield the same y value. So if I do all the points on one side, I can back up and move the y values on this side. Let's take a look at identifying the vertex and the axis of symmetry when it's in standard form. Okay, you should already know how to do the vertex from Algebra 2 from the vertex form. Completing the square may be something that you need work on, but you should have also covered the vertex when I have something in standard form. Is this is the x value, is you take the opposite of whatever b is and divide it by 2a, and the y value is just simply taking what you got for the x value, sticking that x value into the equation. That's why it says f of negative b over 2a. Negative b over 2a is just simply the x value. So I'm really just taking f of x here, and I'm plugging that value in for the y value. So that also is the vertex when it's in standard form. You will be responsible for both. You need to be able to take it from vertex form using this method, but also transforming a quadratic from standard form to vertex form by completing the square. Okay. We just completed completing the square, turning it into vertex form with the standard form quadratic. We actually now are going to look at some other ways of doing this. Okay, so let's take a look at this again. You know its vertex was -2, -3. Okay, I think that's what we got, right? -2, -3. Let's see if we can graph that by using that last method, which means that I take negative b over 2a and f of negative b over 2a. Okay, so that's what we're going to set up here and do in 3, but I'm going to talk about some additional items here, especially when we look at the quadratic formula. If you recall, the quadratic formula looks like this. And underneath the square root, or the radical, we have something called the discriminant. This thing here, b squared minus 4a times c. It's a very important item because it helps you to determine what the solution is, or how many solutions. Basically, how many times the quadratic touches the x-axis. So if I look at the discriminant, I know if the discriminant b squared minus 4ac is equal to 0. So that means you're taking the square root of 0, which means you only have one value. You don't have a plus and minus. This plus and minus gives me the two answers. If this is simply 0, this plus or minus 0 is still 0. So I end up with one solution. So one solution. If b squared minus 4ac is greater than 0, we have two solutions. And you should be able to easily see now that if I have a number that's greater than 0 underneath the radical, that means I'm going to get a positive value and a negative value. Therefore, I'm going to get two solutions. I'm going to get two fractions here that I'll have to evaluate. And then if the discriminant b squared minus 4ac is less than 0, there are no solutions. The reason being is this becomes an imaginary number. You would have the square root of a negative number. Okay? So once again, one solution looks like this. I'm just going to use a parabola up. It touches once. Two solutions would mean the parabola touches the x-axis twice. And then no solutions would mean that the parabola does not touch the x-axis at all. Okay? Let's take a look at x squared minus 6x plus 9. This is in standard form, and we're going to look at the negative b over 2a way of determining the vertex here. First of all, let's answer some questions that I should be able to easily answer. Does the parabola open up or down? Well, you can see the a value is understood to be 1 here. It's positive. So that means the parabola opens up. Looks like this. And we further know, since it's 1, that it has no change in opening faster or slower. It looks like the parent function when it comes to its rise. We need to determine the domain and range. Now, we should be able to easily determine the domain. It's going to be all real numbers. The problem is how do we determine the range? The range will be determined by the vertex and whether this thing goes up or whether this goes down. If you look closely here, the vertex will either be the lowest y value, or if it's upside down, the vertex will be the highest y value. So this would be a max, and this would be a min. Well, if I know how to determine the vertex, I can now determine the range. The range in a min situation will be simply the y value, minimum, and then all values above, which would be infinity. If you have an upside down quadratic, it simply would be the y value for the max, which would be the vertex, and then everything below, which would be negative infinity. Okay? You also need to know where the function is increasing or whether it's decreasing. Well, if I look at a parabola that is U-shaped up, I know that on one side it's doing one thing, and on the other side it's doing the opposite. In the case of U-shaped up, it would be decreasing from negative infinity to wherever the vertex is. And then increasing from wherever the vertex is to infinity this way. Now it's just opposite when it's upside down. On the left side, it would be increasing from negative infinity all the way to the vertex, and then from the vertex to the right side, it would be to infinity decreasing. Okay, so let's answer some quick questions here. We already know what's going on with this parabola in terms of opening up. We don't know its vertex. Once we find the vertex, we can answer other questions. The y-intercept would be easy to answer because it's in standard form. I know that the y-intercept is this value here, 9. The y-intercept is 9, or 0, 9. What's interesting enough, if we find the vertex, this is an additional point because I can reflect this 0, 9 onto the other side using the axis of symmetry. Okay? What's the domain and range? We know the domain of this quadratic, x squared minus 6x plus 9, is all real numbers. The range, we don't know yet until we find the vertex. And we know that the range will go from the vertex from one side all the way up. We know it goes up. We just don't know the y value here for the range. But I do know that it goes up to positive infinity because it's u-shaped up. If it was u-shaped up, then we would be using negative infinity on the left side and then the y value as a max. We know that this is going to be a min here. So I need to find this value here. Once I find the vertex, it will give me the answer to the range, and it will also help me to determine where this thing is increasing and decreasing. However, since this a is positive, I know it decreases from the left. So I know it goes to negative infinity to whatever the min value is. And then I know that this is decreasing here. And then I know it's increasing, if I look up here, at the min value for the y. I don't know that yet until I determine the vertex. All the way to infinity. It's increasing. So this would be increasing. Okay. So let's determine what we have here for my x value, negative b over 2a, and f of negative b over 2a. So I look and I see that b is negative 6. So my vertex is going to be negative 6 over 2a, and a happens to be 1. And then I'm going to plug this number into the function. So I'm going to determine what this is. This is negative, which would be 6. 6 divided by 2 is 3. So this is really f of 3 now. So I know for my x value it's 3. This evaluated to 3. So I have 3. And then now I'm going to stick 3 in this function here. 6 times 3 is going to be negative 18 plus 9. And then 3 times 3 over here will be 9. So if you look, we have 9 minus 18 is negative 9, plus 9 is 0. Okay? So 3, 0 will be our vertex. I should be able to plot this now, draw a graph, but I can answer my questions at least. I know that this is a minimum. So I know that the y value drops off at 0. So from 0 to infinity is its range. 1, 2, 3, and this is 0. I know my y-intercept is at 9. Okay, I know that 1, 2, 3 gives me a y-intercept here. That means I count 1, 2, 3. So this is 1, 2, 3 away. 1, 2, 3. That there's an equal and opposite y value here because the axis of symmetry goes right down the middle of my parabola. So this is my min, 3, 0. So I can see now clearly where it's increasing or decreasing. Decreasing, negative infinity, to this. Now we're using an x value here. Okay, this x value would be 3. And then it's increasing from 3 to positive infinity. Okay, now let me quickly plot this thing. This is not the absolute value. This is from a previous class. We know that we have x squared minus 6x plus 9. And I know that we just determined the vertex to be 3, 0. So 1, 2, 3 is here. We know the y-intercept is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We know that this is the axis of symmetry here. And I know the same distance away from this point here, which is 1, 2, 3, there exists the exact same y value 3 units away from the vertex. 1, 2, 3. So I know that that's a point. Okay. What does that mean? That means when I pick 0, well, we'll figure out what this is here. If we pick 2, the number right before, the number right after is 4. Okay. Now what we're doing is we're going to this number here. This number here is 0, 9. So what I'm doing is backing up symmetrically. This is my vertex. And I know that this point and this x point have the same y values. And then I'm going to back up to 1 and then 5. 1 and 5 should have the same y value. And then 0. I know 0 gives me 9. Okay? That means that 6 is the corresponding x value that also gives me 9. Let's check that out. 1, 2, 3, 4, 5, 6. And yes, it is 6. So this is 3, 0, or 0, 9, and this is 6, 9. What if I put in 2, or what if I put in 4? We should get the same value. Let's try 1 first. That 1 corresponds to 5, gives us the same value. If I put in 1, 1 squared is 1. Minus 6 times 1 is minus 6, plus 9. 1 and minus 6 is negative 5, plus 9 is 4. So 1 and 4. 1, 1, 2, 3, 4. So I should have an equal y value 2 units away from my vertex. 1, 2. Well, let's see if that's true. It appears to be true visually. So if we put in, remember, 5 now. So 5 squared is 25. And then negative 6 times 5 is negative 30 plus 9. Well, 25 and minus 30 is minus 5. Minus 5 and 9, it's 4. So we get the exact same thing. That's just the nature or the property that parabolas have. Once you find the vertex, you know the axis of symmetry, all I have to do is find one point, and I can reflect it the same x units away. So you really don't have to use a table for all the values. If you find 1 or 2 values on this side, I can simply reflect them over to the other side the same distance away from the axis of symmetry. Okay? You can do the same for 2, and it will be the same for 4. So what we found for 5 was the same for 1, which was 4 as well. So that concludes the instruction for 3.3. Enjoy.